Hello, grade 9 students. Welcome to School on Air Science 9. Once again, this is teacher Sherry May serving you. We are now in week 3 of quarter 4, and in this week's lesson, it's all about momentum and impulse. So, grade 9 students, are you ready? Let's check out first our objectives. Number 1, define momentum and impulse. Number 2, calculate momentum and impulse. And number 3, relate momentum and impulse to collision of objects. We will be listening 3 lectures today. The first one is about momentum, followed by the lecture on impulse, and the third one is the lecture on the relationship between momentum and impulse. So, ladies and gentlemen, this is it.
Hi, it's Mr. Anderson, and this is AP Physics Essentials video 49. It's on momentum, which is just the product of the mass of an object times its velocity. In 1895, a train was headed towards Paris. They were a little bit behind schedule, didn't apply the brakes in time, and it came shooting out through the train station. What was their problem? They had too much momentum. And if you were to ask somebody, what is momentum? They'll probably come up with a pretty good definition that would fit in physics. Momentum is always going to occur if we have an object that's in motion. And if you want to calculate it, you simply multiply the mass of the object times the velocity of the object. The greater the mass, the greater the velocity, the greater the momentum is going to be. And so if we want to change our momentum, what could we do? Well, we could decrease the mass, we could increase the mass, or we could change the velocity. What's the easiest way to change the velocity is to apply a net force to that object. If we apply a net force to the right to this object, what are we going to see? We're going to see an increase in momentum towards the right. Let's say the object is moving towards the right and we change the net force on the object. What's going to happen? It doesn't happen instantaneously, but what we'll see is a change in momentum that reflects that net force. And so if we define momentum, the equation is P equals mv, where we're multiplying the mass of an object times the velocity of the object. So if we have this cart here, a 1.0 kilogram cart, and it's moving with a velocity of 2.0 meters per second, figuring out its momentum is really easy. You simply multiply 1.0 times 2.0, and so our momentum is going to be 2.0 kilogram meters per second. And so if we add velocity to the right, we're going to increase that momentum. Now, one thing that you need to remember is that the net force on an object is going to affect that change in P, or that change in momentum. And so let's say we have an object like this, a cart that's at rest. It has no momentum, but we apply a net force to it. How would we do that in a physics lab? We're just going to connect it to a weight. And so now we're going to apply a net force to the right. What's going to happen to our momentum? It's going to increase to the right. What happens if we increase that net force? If we double the net force on the object, what's going to happen? We're going to increase the momentum more quickly. Let's say we triple it, we're going to see an increase in momentum to the right. And so it's a direct relationship between the net force on an object and the momentum on that object. But let's make it a little bit trickier. Let's say that object is moving now towards the left, but we're applying a net force to the right. What's going to happen? Well, eventually what's going to happen, let's watch, is it's going to slow down and then it's going to start to accelerate to the right. And so even though it was moving to the left, as we apply a net force to it, eventually that momentum is going to move in the direction of the net force. Now these are pretty easy problems because we're just looking at one dimension. But when you were growing up, like me, you probably played video games like this. And so if I turn the ship and move it in this direction and blow up an asteroid, it's all momentum. But I would find myself playing asteroids like this. I'd be moving in one direction, but I'd be applying a force in another direction. In other words, my momentum is in that direction, but my net force is in a totally different direction. What's going to happen to that? Well, it doesn't happen instantaneously, but what's going to happen is that ship is eventually going to move in the direction of the net force. And so did you learn to justify the data we need to collect to show that the net force eventually impacts the change in momentum? I hope so, and I hope this was helpful. Hi, it's Mr. Anderson, and this is AP Physics Essentials Video 50. It's on impulse, which is simply the product of the force being applied times the time over which that force is being applied. And so let me give you a scenario. Imagine we have a baseball here that's moving from the left towards the right, and so it has momentum towards the batter. And let's say he hits it. Well, what's going to happen to the momentum? It's going to change dramatically. It's going to go in the opposite direction. What's causing that, however, is the impulse. The bat is applying a force over a given period of time. And what's interesting is that the change in the momentum and the impulse are equivalent. What does that mean? They're always going to give you the same value, and that makes them really valuable when we're looking at physics. And so let's look at two spheres that are being dropped on a table. Let's imagine that they both fall with the same velocity and they both have the same mass. So watch what happens to the first one and then the second one. And so a good question might be, which has experienced the most dramatic change in momentum? That's kind of a trick question. Since they both have the same mass and the same velocity, and at the end they're at rest, they've experienced the same change in momentum. Therefore, their impulse is the same. And so what's different in these two spheres as they fall to the table? Well, it's the time over which they interact with the table itself. The one on the right is really slowing down over a longer period of time. And that means it's applying less force to that table. And so momentum will change over time. And so if we have these two spheres, the momentum is going to be the same between each of those. The impulse is also going to be the same. What's the impulse? It's simply multiplying the force of an object times the time of that object. And these are equivalent. The change in momentum and the impulse are exactly the same thing. And so what's different in these two spheres? Well, in this sphere right here, what we're getting is a really large force over a short period of time. And this one, we're getting a really short or a small force over a long period of time. And that fact is so important that it could literally save your life. Cars have gotten safer and safer over time. And so this is a safety video. If we were to crash a 57 Chevy, an old car, into a wall at 35 miles an hour, the person inside would really be hurt because it's going to come to a stop almost instantaneously. But watch what happens when this Honda Civic is driven into a wall at 35 miles an hour. Again, it's slowed down, but watch how long it takes for that car to come to rest. And so it's like that squishy ball. It's taking a longer period of time for it to change its momentum. And so we're decreasing the force experienced by both the car and the person inside the car. And so to figure out how these two are related, it's really simple. And it begins, like everything in physics, with Newton's second law, which is force equal to mass times acceleration. But let's break down acceleration, which is simply going to be the change in velocity over time. Now I'm going to take both sides of this equation and I'm going to multiply them times time. And so if I do that, what do I get? The two subjects of this video. Momentum change, which is mass times the change in velocity. That's on the right. What's on the left? That's going to be the impulse. And these are equivalent, so we can use it to solve really difficult problems. Like, could you calculate the impulse and the force on both the car as it crashes into the wall and then the crash test dummy on the inside of the wall? Well, you'll be able to, and we'll work through a few problems like that. And so if you want to figure out what we need to solve a problem like that, it's all given in the equations up here. Mass times change in velocity, force times time. But we're just watching a video here, so you don't see any force in the video. And so we're going to have to solve for that in a little bit of an indirect kind of a way. And so what would be the first things that we could figure out? Well, we got to figure out the mass. And so I could just give you the mass. The mass of this car, which is a 2013 Honda Civic Hybrid, is 1,301 kilograms. And the mass of the person inside the car is around 78 kilograms. What else could I tell you? Well, we know this car is going at 35 miles an hour, and at the end it's going to be going 0. And so we could see a change in velocity of 15.6 meters per second. What else do we have to figure out? Well, it'd be important for us to figure out time. This information right here is enough for us to figure out the momentum change and the impulse. But if we want to get at the force being applied to the car and the crash test dummy, we also have to know the time. And so let's watch the video and let me show you how you can figure this out. So we've got the car crashing into the wall. I'm going to grab the video right here. And you can see here that right at this point, at time 0, it's impacting the car. And we've reset our time to 0. And so what I want you to do is let's watch a section of the car. Let's watch this section of the car right here. And let's see how long it takes for that car to come to rest. And so again, we'll go back to 0. So it's now at 0. So we're at 0 here. And so just watch the car and figure out how long it takes for that car to completely come to rest. So let me keep moving. So right about there. So right about there, the car has stopped moving. And so we could say that that change in time is 0.072 seconds. I'm getting that right here. But if I keep playing the video, you'll see that that person continues to move. They're still moving forward, and they don't come to a stop until around here. And so we could say their time of impulse is going to be 0.112 seconds. And so let me give you a simple problem. What I want you to figure out is calculate the impulse and the force being applied to both the car and the man sitting within the car. And what I would encourage you to do is pause the video right here. You have everything you need right up here. I would grab a piece of paper and try to work this out. Again, you're going to have 4 values when you're done. Impulse of the car, force on the car, impulse on the man, force on the man. And so pause the video, try to work that out, but I'm going to show you how to do it right now. And so what you would do if we're trying to figure out the impulse on the car, all you need is the mass of the car and then that change in velocity. And so impulse is equal to the mass times the change in velocity. So I'm simply putting in the mass right here of 1,301 kilograms, the change in velocity of 15.6 meters per second. And so my impulse is going to be this, newtons per second. Now how did I get that? Well, since it's a force times the time, it's going to be newtons times seconds. You can see here that this number has way too many significant digits, and so I could reduce that so that it has 3 significant digits, and that's the answer of the impulse on that car. Now, how do we figure out the force being applied? Well, since I showed you the time, 0.072 seconds, if we want to figure out the impulse, all we do is simply divide by the time. So if we divide it by the time, it's going to give us the force that's being applied. So I'm going to take that impulse, which is right here. I'm going to include all those significant digits. And then I'm going to divide it by the time, which is 0.072 seconds. It's going to give me a force of that. And then, again, too many significant digits, I can figure out my force, which is only going to have 2 significant digits. And so it's going to be 2.8 times 10 to the 5th newtons. Why is that? Because 0.72 only has 2 significant digits. And so that's a massive force that's being applied to that car. But since the time is greater than it would be with an old car, it's actually going to be a much smaller force you would experience in a new age car. Let's say we were looking at the person inside it. How do we figure that out again? Again, you could stop right now, and if you want to try to solve this one, you sure could. We're going to start with the impulse, which is simply going to be the mass times the change in velocity. And so I could figure it out like that. With significant digits, it's going to be 1.2 times 10 to the 3rd newtons seconds. That's going to be the impulse. If I want to figure out the force, all I'm going to do is going to be to divide by the time. And so that's going to give me a value of around 1.1 times 10 to the 4th newtons. And so that's going to be the force that is applied to that person. Now that's not a deadly force, and the reason why is that we've increased that amount of time. Even though the momentum and the impulse stay the same, by increasing the time we can decrease the force. And so did you learn to justify the selection of data if you want to figure out the impulse or if you want to figure out the force? And then finally, could you predict, analyze, and design a plan for collecting data? In this case, we used a video to look at the change in that momentum over time, but you could use a ticker tape, you could use a motion sensor to figure this out. So that's impulse, again, product of force times time, and I hope that was helpful.
us start with momentum and impulse. Suppose you play basketball with your friends. What will happen to the ball if it hits the board instead of inside the ring? How about if you bump into another player that is bigger than you? These questions will be answered as you go along with this video lesson. One of the most common team sports is basketball. Imagine two teams who are involved in a really tight tournament quarterfinals. Team A has 2 points ahead of Team B. Later on in the match, a player from Team B scores a 3-point shot and followed by a series of 2-point shots. Team B couldn't stop their momentum. And what do you mean by momentum? In our example a while ago, these are the things that we need to consider in defining momentum. First, the object has a mass. And second, the object is moving. Any object with a quantity of matter has momentum. And momentum simply means mass and motion. It is equal to the product of mass and velocity. Mathematically, it is expressed as P is equal to M times V, where P is the momentum in kilogram meter per second, M is the mass of the moving object in kilogram, and V refers to the velocity of the moving object in meter per second. Let us try to solve this problem. Sample problem 1. What is the momentum of a 22 kilogram grocery cart which travels at 1.2 meter per second? First, let us have the given. The mass of the grocery cart is 22 kilograms. It travels with the velocity of 1.2 meter per second. And we are looking for the P or the momentum. Here's our formula. To get the momentum, we need to get the product of mass and velocity. Now, let us solve this problem. Our solution, P is equal to the mass, which is 22 kilograms, the velocity, which is 1.2 meter per second. Multiplying these two, the product is 26.4 and the unit is kilogram meter per second. Take note how you write the unit for momentum. And this is our final answer. Next, how about the momentum of an object that is not moving? Just like a car that is parked. Remember, class, if any object of any mass is not moving, it has zero momentum since its velocity is zero. Let us consider another situation and try to answer the given questions. Suppose you ride a bus from Iligan City to Cagayan de Oro. What do you think will happen to the bus after it passes along a curvy road? Will it slow down? Will it speed up? Or the velocity will not change at all? If your answer is letter A, then you are correct. The bus will slow down if it passes along a curvy road. Next question. After passing curvy road, the bus travels in a straight road. How will you describe the velocity of the bus? It increases, decreases, or not change at all? If your answer is letter A, then you are correct. After passing curvy road and travels a straight road, the velocity of the bus will increase. Next, there were only 25 passengers in the bus. Along the way, 4 passengers dropped at Lagindingan bus stop and another 4 passengers dropped off at Opol bus stop. What can you say about the mass of the bus? It increases, decreases, or not change at all? If your answer is letter B, then you are correct. The mass of the bus decreases. Based on our example situation, we can say that when the object slows down or moves faster, its velocity decreases or increases. If there is a change in the velocity of the mass of an object, there is also a change in momentum. And that change of momentum is what we call impulse. Impulse is equal to the change in momentum. And it is represented as letter I. Again, class, impulse is equal to the change in momentum. And remember, class, that momentum is equal to the product of mass and velocity. Just like our example, there is a change in momentum. And for that to happen, force is needed to change the momentum of a body. This force multiplied by the time of contact is known as impulse. Impulse is equal to the product of force, which is expressed as capital letter F, and time, which is expressed as small letter t. Analyzing these concepts, class, we can say this equation. Since impulse is equal to the change of momentum, and momentum is the product of mass and velocity, therefore we can say that impulse is equal to the product of force and time and mass and velocity. The standard unit for momentum and impulse is Newton second or kilogram meter per second. Take note, class, bodies change their momentum through collisions, which may be elastic or inelastic. Let us have a sample problem. Sample problem number 2. An offensive player passes a football of mass 0.42 kg with a velocity of 25.0 meter per second due south. If the player is in contact with the ball for 0.050 seconds, what is the magnitude of the average force he exerts? Here are the given for our problem. The mass of the ball is 0.42 kg. Its velocity is 25.0 meter per second south, and the time contact with the ball is 0.050 seconds, and we are looking for the force. Remember, class, our formula for the impulse? Impulse is equal to the product of force and time, which is also equal to the product of mass and velocity. Since we need to determine the force, we can do some algebra with this equation. Using division property of equality, let us divide t both sides, and we can cancel out time on the left side of the equation. Therefore, we can get this formula. Force is equal to the product of mass and velocity divided by time. Now, let us solve this problem. For our solution, let us substitute our given to our formula. Force is equal to the mass, which is 0.42 kg, our velocity, which is 25.0 meter per second, all over our time, which is 0.050 second. 0.42 times 25.0, we have 10.5, and our unit, kilogram meter per second, divided by 0.050 second. Dividing these, the quotient will be 210 kilogram meter per second squared. And this is our final answer. And that is how you solve this kind of problem. Rearranging our equation will help us understand how impact force is affected by the change in momentum and the time of contact. It shows that the force of impact is directly proportional to the momentum of the body and inversely proportional to the time of contact. We can say, for example, that the impact force of a fast-moving car is higher, and therefore it can cause greater damage after the collision than the car moving at a lower velocity. On the other hand, the equation also tells us that the impact force could be decreased by extending the time of contact. That is why cars are designed with airbags, because it can lessen or prevent injuries in the event of crash or collision. The inflation of the airbag is initiated by crash sensors. This decreases the impact force by increasing the time of contact. Next, let's have some example scenarios exhibiting impulse. What do you think is the impulse of an object moving with constant momentum? Constant means no change at all. Therefore, there is no impulse or zero impulse for objects moving with constant momentum. Take note of that, class. You now know that any object has momentum, and it is equal to the product of mass and velocity. Impulse, on the other hand, is a change of momentum of a moving object. Next, what will happen to a moving object if it collides with another object? Let's have this scenario. Suppose you are playing billiard. The cue ball and ball number 1 are initially at rest. Then, you use the taco to hit ball number 1. Based on the given illustration, answer the following questions. What did you observe on the mass of the cue ball before and after collision? There is no change in mass. How about ball number 1? Also, there is no change in their mass. Question number 2. Since it is initially at rest, what are the initial velocity of the balls? The answer? 0. Question number 3. After collision, is there a change in velocity of the cue ball and ball number 1? The answer? Yes. Question number 4. Is there a change in momentum of the cue ball and ball number 1? And why? Since there is a change in the velocity, of course, there is a change in momentum. Therefore, there is impulse because there is a change in momentum. Since the cue ball and ball number 1 have a change in velocity after collision, then both balls have a change in momentum. Also, in collisions, an object that experiences a greater change in momentum has greater impulse. Therefore, this shows the relationship between impulse and momentum, that a change in momentum is equal to impulse. Let's have another scenario. Suppose that two cars with equal masses collide with each other. Car A travels faster than car B. They both stop after collision. Note that the bigger the letter of velocity or mass, the greater its value. And in this scenario, the greater velocity is car A. Now, given this scenario, which of the two cars has the greater change of velocity? The answer is car A. Next, which car has the greater change in momentum? Explain your answer. The answer? Car A, because it travels faster than car B. Therefore, it has greater velocity. Remember class, greater velocity means greater change in momentum. Next question. Which car has the greater impulse? The answer is car A because it has greater change in momentum. In other words, the object that experiences a greater impulse is the one that has the greater change in momentum. And that ends our lesson about impulse and momentum.
Thank you so much, dear students. I hope you learned something new today. If you have questions or queries, so you can ask your learning facilitators at home, your parents, brothers, sisters, lolos or lulas, or you can text or send an email to your teachers. For this RBI segment, once again, thank you to DepEd Dapitan City, headed by Dr. Felix Romy A. Triambolo, OIC City Schools Division Superintendent. And thank you LGU Dapitan City, headed by Honorable Rosalina G. Haloshos, the City Mayor. Thank you very much. This is all for today, students. Thank you for your time. If you have questions, feel free to ask your learning facilitators at home, your parents, sisters, and brothers, or you can send an email or text to your teacher regarding your queries. For this RBI segment, thank you DepEd Dapitan City, headed by Dr. Felix Romy A. Triambolo, OIC Schools Division Superintendent, and thank you LGU Dapitan City, headed by Honorable Rosalina G. Haloshos, the City Mayor. Keep safe, everyone. Bye-bye. Thank you very much. This is all for today, students. Thank you for your time. If you have questions, feel free to ask your learning facilitators at home, your parents, sisters, and brothers, or you can send an email or text to your teacher regarding your queries. For this RBI segment, thank you DepEd Dapitan City, headed by Dr. Felix Romy A. Triambolo, OIC Schools Division Superintendent, and thank you LGU Dapitan City, headed by Honorable Rosalina G. Haloshos, the City Mayor. Keep safe, everyone. Bye-bye. Thank you very much. This is all for today, students. Thank you for your time. If you have questions, feel free to ask your learning facilitators at home, your parents, sisters, and brothers, or you can send an email or text to your teacher regarding your queries. For this RBI segment, thank you DepEd Dapitan City, headed by Dr. Felix Romy A. Triambolo, OIC Schools Division Superintendent, and thank you LGU Dapitan City, headed by Honorable Rosalina G. Haloshos, the City Mayor. Keep safe, everyone. Bye-bye.